Hi everyone, today we're gonna look at beam deflection by double integration method. So I'm gonna go through some examples, and hopefully through these examples we're gonna know how to express the deflection of a beam using the double integration method. So in this example one, what we have here is that we have this force P, and it is acting at a distance of L along the cantilever. So you have to establish the equation for the elastic curve. We have the EI, which is the flexural rigidity, E is the elastic modulus, and I is the moment of inertia. We have it as constant, of course, just along the beam, and I'm not changing the cross section along the beam, and I'm using the same material, so it is a constant. Now, in order to find the deflection of this beam, the equation of it, well, we have to find the boundary conditions. First of all, if you just draw the deflected shape, it's going to take this shape, as you can see here, and obviously what you can tell is that we have the maximum deflection at the end tip. And what I can tell here is because I'm having a fixed end support, so that tells me as well that I have a zero slope, as well as you have a zero deflection. Here you have the maximum deflection, but here you don't have any deflection, so the deflection is zero here. The double integration equation, it is derived using the curvature. I'm not going to go through that theory, but this is what you need to work with in order to find the deflection of a beam. What I can tell here is that, well, I have the moment here, and I have the flexural rigidity, EI. So, well, simply I can say that the internal moment, this is the mx, it is the internal moment as a function along the x coordinate of a beam. I'm going to talk more about this. And flexural rigidity, I already said that it is a constant along the beam. So this is the curvature. This is all based on assumptions, and the assumptions are that we are dealing with linear and elastic behavior, so there's no like such a plastic behavior here, and the deflection is small. So based on these assumptions, we can use this curvature or the double integration equation in order to find the deflection of a beam. So from example one, we can just follow the steps. We can first of all establish the x and y coordinate axis, and then we can express the internal moment as a function of x, and then we just apply the double integration equation. We're gonna need to solve the constants using the boundary conditions. And just a quick note here, I can just represent the horizontal axis as x and the vertical as y, but instead of writing y, I can just write it as v, just to indicate the deflection. Right, now before going through solving the example one, we need to just clarify some stuff here. So well, suppose that I have the same example as the same example one. I'm having this point load at the end tip, and if I want to find the moment as a function of x, what do I have to do? First of all, I said we have to establish the axis. So I have the x-axis here and the v-axis here, or the y-axis. It's up to you. What I want to do here is that I want to find the moment along this beam. So I'm going to take a cross section here, and if I zoom in a bit, I'm going to have this beam. Okay, you have to include the force there. So this is the P, the force applied, and well, the internal forces, I'm having a moment, and I'm having a shear force as well along the beam, right? The only thing that you have to note here is that, well, it is from here, so this is the origin, so this is where we have the x as 0 and y as 0, or the v as 0. So what I have to write here is that I have to represent the distance, this chunk, so it is L minus x. Okay, so this is L minus x gives me this distance, and well, I can then compute the moment. So I'm taking the moment at this point. So what I have here is that I have the internal moment, so this is the M, and I have this force as well. It will generate a moment in the same direction of the internal moment, so it's going to be P times L minus X. I'm just taking the P times L minus X to the right side, and just in order to really simplify this, what I get there if I apply a load here, I'm gonna get a negative bending moment, right? I'm gonna have a hogging bending moment. So that tells me that, well, this is a good indication because I'm writing a negative sign here, and that is because along this beam, if I find the moment along this beam, it's going to be a negative moment. It's going to be a hogging moment. So, well, this is just to make sure. Okay, this is from the bending moment diagram. And, well, you might say that, is the system in equilibrium? Yes, it is. See, the internal moment is acting within the force, so they are acting in the same direction. But this will be resisted by the support, of course. We are talking about static equilibrium. So the bending moment will be anti-clockwise to resist this clockwise moment, and the shear force as well. So we have it here as downwards, and we have it here as upwards. So this is how to compute the bending moment as a function of x along this beam. But what if we have a simply supported beam with a UDL? Well, we do the same thing. So I'm gonna take this portion of the beam. So remember, it is towards the x-axis. So that means if I'm gonna zoom in, the distance here gonna be x only. I can do something here. So instead of writing the UDL, I'm just gonna write it as a point load. It will act as at the mid of this distance. So it is Wx. First of all, I have to convert it into a point load. So it is W times x. It will be acting at a distance of x over 2. And then, well, I have the bending moment. Of course, if I take a cross section here, right, I'm gonna have this internal moment. So this is acting anti-clockwise. I also have this, the one I converted into a point load, it is also acting anti-clockwise. The only moment that is acting clockwise is the reaction, the force I have at the support. So it's just simply WL over 2 at a distance of x. So this is the force times the distance gives me the moment, and it is acting clockwise, so I'm giving it a negative sign. So simply simplified, rearrange, and what you get here is a positive sign. So this is a good indication of a sagging moment, just to make sure. So I have a sagging moment, of course, and this is why I'm having a positive sign here. Right. With that all being said, I can just proceed. So I'm establishing my axis. So this is the V and this is the X. I'm gonna take this cross section. I'm gonna take this section N. Let me just call it N. And then I'm taking this portion. Of course, you need to include the force P. And zoom in. What you get is, as what I said, this is the distance L minus X, and I have all the forces. So the moment can be expressed as minus P times L minus X. There's another thing. Well, I can mirror my cantilever. It is absolutely correct. So I'm not changing anything. I'm just mirroring the cantilever. And well, in this case, the only difference here is that, remember, my origin is here, right? So what do I have here is that I have the distance as x. It is no longer L minus X, right? So this is the X, and I have the same forces as well. So my bending moment equation, so it is simpler. It is only minus P times X. So if I carry on this, that is absolutely correct. And if I take the one I showed you previously, that is also correct. So I'm gonna go with the one I did at the beginning. So it is minus p times L minus x. So, well, I can take the EI to the left hand side because it's a constant, and the bending moment, so it is just simply the one we derived. And then once I integrate it once, okay, I'm gonna have a constant C1. So the C1 has to be found using the boundary condition. What is a boundary condition, right? Look at my cantilever. At the support, what do I have? I have the slope to be 0, and remember the slope is the dv over dx simply, right? And this is at a distance of 0, okay? And if I apply this boundary condition, so the slope dv over x, instead of writing the dv over x, I'm just writing it as a 0. It is at a distance of 0. So instead of writing x here, I'm going to write 0. So simply, I'm going to end up having the first constant as 0. So that was the first boundary condition. And the second boundary condition is, well, I have the deflection as 0. The only thing here is that I have to integrate it once more. Okay, so this is the one with the C1 equals to 0. Okay, this is a slope. And if I integrate it once more, I'm gonna have the deflection. So this is the V, this is my deflection. And well, I'm gonna have another constant, C2. In order to find this constant, well, I have to apply the boundary condition. And here I have the deflection as 0, okay, at a distance of 0. So the x is 0 here. And once you apply this, simply you're gonna end up having the C2 as 0. Okay, so let me just sum up all of this. So, well, simply the V, so the constant C2 is 0, so I can express it in this way. And it's always a good idea to simplify it, just do the math there. And well, I can also find the maximum deflection. Well, I know that the maximum deflection gonna be here, right? This is where I have the maximum deflection at a distance of x equals L. Okay, this is the L. And well, I can just put it in this way. Instead of writing the L, I'm gonna write instead of writing x as the one you can see here, I'm gonna write it as L. So put the L there, plug and check, you can get the Vmax, and the Vmax here is at a distance of L, so it is going to be P times L cube over 3EI. If I want to find the deflection, well, say at this point or at this point, when I know the x, say 2 meters, 3 meters, well, in that case, I can just apply this expression. So it is x larger than 0, but less than L. Let's get into the second example. So here we have a simply supported beam, and well, I have this force P, okay, acting at the midspan, so at L over 2. Well, I have to find I have to establish the equation of the elastic curve. And well, first of all, establishing my axis. Remember, a good general practice is that you take it from the left hand side, so it is from here. Make this your origin. Try to draw the deflected chip. It is always a good practice to draw the deflected chip. The boundary conditions, simply I'm gonna have 0 deflection here as well as 0 deflection here. So the only case is this is at a distance of 0, and this is at a distance of L. So first of all, we have to find the internal moment, and if I take this portion, well, I can take this portion or this portion. Okay, so I'm taking this portion. Well, you might say that you're not including the P. No, the P is included. It is here. The P is here. So I'm taking this portion. Remember, it is towards the origin, so it is at distance x, and simply R1 is going to be the same as R2 because I'm having the P at the midspan. So I'm having a symmetrical load. So here we have the forces. If I express the moments, the moments have the sum of the moments must be 0. Here's my moment. I'm taking the moment at this section, and I have this moment, right? And the one I have it here acting in the opposite direction, so I'm giving it a negative sign, and simply p over 2 times the distance of x. So my moment as a function of x is going to be the one you can see here. What if I take this portion? Well, simply the same thing exactly, except that the distance here is no longer x. L minus x gives me the L minus x here, and well, simply exactly the same procedure. So I'm gonna go with this simple bending moment equation, and let's see. So this is a curvature, and I'm gonna integrate it. Simply this is gonna be p over 4 times x squared plus the phase constant c1. Now I talked about the deflection, as the deflection is going to be 0 here, right? At the both ends. But that's the deflection. What I have here is I'm having the slope, dv over dx. And how would I compute the boundary condition if I only have the deflection? Simply, for a simply supported beam, at the midspan, exactly at the midspan, I'm also having the slope, right? If you just draw a straight line here, you're gonna find that the slope is 0 here, and this is at a distance of L over 2. Alright, so the slope is 0 at a distance of L over 2. So I can use this piece of information to find the C1. So I'm gonna write this as 0, and instead of writing x, I'm gonna write L over 2. So that gives me the phase constant, right? So I'm just putting the C1 into this expression, so I have it as the one you can see here. Okay, let's carry on. So I'm gonna just simplify it. So I'm ending up having this expression. This is my slope, but I don't want the slope, I want the deflection. So I'm gonna integrate it once more. That gives me another constant, C2. So simply, C2 is going to be 0. Why? Because I'm using this boundary condition. And remember, at the support I have a 0 deflection. So it is either I take this one or this one. Go for the simpler one. So this is my deflection. I can simplify it, get it in this form. This tells me how to find the deflection along the beam. So at this distance, or at this point, or at this point, but the maximum one is obviously at the distance of L over 2. And of course the negative sign here is just an indication of the, it is downwards, so it is, we give it a negative sign, right? So this is the third example, and simply I'm having this simply supported beam with the UGL. I already worked out the moment, the internal moment as a function of x. Just go back to that slide, and simply, so this is my bending moment. I'm gonna integrate it to find the slope, and I'm gonna have this C1. It is exactly the same boundary conditions that we had previously in example 2. I can work out the C1. So this is my constant, the first constant, C1. I'm gonna integrate it. I'm gonna simplify it. But remember, again, we don't want the slope, we want the deflection. Gonna need to integrate it once more. That's gonna give me another constant, C2, using the boundary condition, of course. I'm using this boundary condition here. My constant C2 is going to be a 0. So I can express it in this way, and I can find the maximum deflection at a distance of L over 2. Right. Let me just talk about the cases when loads are not symmetrical. So suppose that we have this B acting a distance of A, and that, what I can say here is that the moment at the section is not going to be the same as the moment at this portion. The P here, if I find the reactions at the support, okay, or suppose at the support A, the reaction would not be the same as the reaction at the support B. So that means if I take a cross section here, I'm gonna end up having a moment different from a moment at this section. So that makes it really tedious and lengthy. Because I'm gonna introduce 4 constants. Remember, at this portion gives me 2 constants, C1 and C2, and this portion will give me another 2 constants, but they are not the same as the one here, so C3 and C4. So it's going to be tedious and lengthy. We can solve it, but there are other methods. It is the Macaulay's method, or the function of singularity. So instead of using that method, double integration method, I can just go ahead and use the Macaulay's method instead. So hopefully we're gonna make it in another video, how to use the Macaulay's method in order to find the deflection of a beam.